In this section, we're going to go over the written solution to the validate function. Like I said at the end of the last video, this is a rather challenging problem, especially because it makes a use of recursion. But we'll go through it nice and slow and hopefully make sense of every step along the way. So I'm going to give myself a little bit of space here and we'll get started. So as we had said, whenever we are calling the validate function, we are going to use this function right here to recurse through every node of our tree. So this validate function is going to end up being called many times as we attempt to validate the tree. Now, as we recurse through and we call validate over and over and over again, we want to somehow pass some information to each subsequent call along the tree. So like we had said, during the first step, going from the root node right here down to the left-hand side, we want to make sure that the next node, or this 0 node right here, understands that the maximum value that it should see should be 10. Remember? So when we go from 10 right here down to 0, the absolute greatest value that we should expect to see from any node in this set right here should be 10. So in order to communicate these minimum and maximums to each recursive or subsequent function called to validate, we're going to add on 2 additional arguments to the function. We're going to add on an argument to reflect the minimum from this point on and the maximum values from this point on. So those min and max are going to be these 2 variables right here. Now it's really important to recognize that min and max can potentially change at any given stage during recursion. So anytime we move to the left, we're going to expect to see the max value to update, and anytime we move to the right, we're going to expect to see the minimum value update. Now the next thing we need to keep in mind as we start thinking about this argument list right here is what happens the very first time we start to recurse through our structure. So in other words, as soon as we start going from the root node down to the left-hand side, we have said several times at this point that we will update the value of max. However, we haven't said anything about the value of min. Anytime we move to the left, we aren't going to update min at all. So I think that maybe we should default the values of min and max and make sure they have some reasonable defaults so that we can look at those values and understand whether or not we have updated them yet. Because in the case that we move from 10 down to the left right here, it actually is kind of important to make sure that we understand, like you and I, we understand that we have not yet set a minimum value for anything on this side of the tree yet when we start looking at 0. So in order to make sure that's clear, we're going to default the value of min to null and max to null. So now when we move from here to here, we will have a max set, but min will be set to null. And so we will know, you and I will know, that we should not attempt to apply any type of minimum value to 0 yet. Okay, so that's step number 1. Hopefully that's not too bad. Now step number 2, we're going to immediately start to inspect the value at the current node that we are iterating over and compare its value to the min and max arguments that are being passed in. Now we've not yet added any logic to actually specify what these values should be. We're going to do that in a little bit. But I think you can agree with me that at some point in time, we need to do the actual comparison of the current node's value to min and max. You know, we need to do the comparison at some point. And so that's what we're going to do right now. So we'll first handle the case in which we move to the left-hand side of a given node. And remember, whenever we move to the left, we are really concerned about the max value. So if max is not equal to null, so this would handle the case in which we have not yet set a max bound, and node.data is greater than max. So if we have a max value and for some reason the current node is out of bounds of that value, then something is definitely wrong with our tree and we should probably immediately return false. And then we're going to do the exact same thing with the min value as well. So we're going to say if min is not null and if the current node's data value is for some reason less than the absolute floor that we should expect to see here, then we need to also return false, like so. Okay, so at this point, with just this code right here, we at least have something to call and compare the current node's value. That's good, but we do not have anything yet to actually initialize or set, not initialize, excuse me, but anything to set the minimum and maximum values. And then we also do not yet have anything to actually recurse through our structure. So to actually do the recursion, we're going to add on 2 more if statements. So in each of these statements, we're going to consider a movement to the left-hand side and a movement to the right-hand side. So let's do going to the left first. So if there is a node to the left of the current node, so this is going to be a check to see if there's anything there, to see if it's not null. So if there's something there, and then this next part is the part that's going to be really kind of tough to wrap your head around, but just bear with me. If calling validate with the node on the left and some minimum value, and then a maximum value of the current node's data, if this right here returns false. So if this right here returns false, we are going to flip it with the exclamation, and that will turn it into a true value. So in other words, if there's a node on the left and calling validate with the node on the left with these new bounds right here returns false, then something really went wrong, and again, we need to return false. All right, now let's do the counter, or the opposite side of this, where we handle the right-hand side, and then we'll be able to kind of talk about what exactly this is doing right here. So we're going to also write out the right-hand side. We'll say if node.write, and if the opposite of validate, so if calling validate results in some falsy value, node.write, node.data, and max. And then inside of here, again, we'll put return false. And then the last thing I want to do, and then we'll talk about the entire solution, if all these if statements all line up okay, then we will return true instead. Okay, so let's talk about what's going on here. So hopefully you're with me on these if statements right here, right? These aren't the worst thing in the world. I think where things start to really go out the window is on these 2 validate function calls. So the first thing that I think is pretty obvious is that the validate function calls right here and right here inside these if statements are what cause the actual recursion to occur. That part makes sense. Now let's talk about what's going to happen if we run through this tree right here with those recursive function calls. And specifically, let's just start off at the very top and walk through this code. So I think that the best way to do this is maybe something like this. I don't know. Let's try it. Yeah, this will work. Okay, so we're going to call validate with the root node of 10 up here. So we come into our function with a node. We do not yet have a minimum or a maximum set. Because minimum and maximum are currently set to null, we skip both these if statements. Like I had said previously, for the top node, for the root node, there's really no validation to do. Really, the root node can have any value, and we're really just going to accept it as being okay. So for the root node, nothing really happens. It's these 2 if statements where things start to get a little bit interesting. So we're going to first say, okay, is there a node to the left-hand side of the root node? And the answer is yes. We have a node there with a value of 0. So we then call validate with a node on the left with a minimum of null. So remember, min is still null right now, but it gets a maximum of node.data. So we call validate with the left node, a minimum of null, and a max of 10. So let's now go down into node 0 with those arguments. So we now have node for 0, min is still null, but max is 10. So at this point, max is no longer null. So we say is node.data greater than max, or greater than 10. For node 0 right here, no, that's not true. So we do not try to enter the return false case. Min is still equal to null, so we skip past that if statement, and then we come down to these 2 if statements again. Now, just for the sake of kind of getting through this diagram, let's assume that this is the entire binary search tree right here. And so let's assume that 0 has no left or right properties defined. So left, right here, the left check fails, we don't enter that statement. The right check fails, and we don't enter that statement, and so we return true. Remember that when we return true, that was for the initial validate function call right here. So when we were still in node 0, we called validate passing in node 0. So when we called validate, that call resulted in true. So we flip true to false, and we do not satisfy this if statement for node 0, or node 10 at the top. We then go down for the original node 10. We're back into that function call at node 10, and we start looking at the right-hand node. We again call validate with node.write, so we pass in 12. We now set a minimum of 10, and a maximum is still null. Remember, the max is null because we had only set the max when we progressed down the left-hand side of the tree. When we progress down the right-hand side initially, we have not yet set a maximum value. So we go down to the right-hand side over here. So let's go back up to the top. We now have a node for 12, our minimum is 10, and our max is null. Max is null, so we don't care about that. Min is not null, so we make sure that 12 is, the current node's value is, gee whiz, oh man, I'm getting myself mixed up here. Okay, my mistake, we set a minimum of 10, and we check to see if the current node's value is less than min. Yes, that is correct. So we check to see if 12 is less than 10. It is not, so we do not enter the if statement. Yes, there we go. So then we go back down here. The node 12 does not have any left or right nodes, so we go to return true. Remember, that now kicks us back up to the original node 10. We say true and opposite of true because we have the exclamation, so that turns into false, so we do not enter the if statement, and eventually we finally hit the return true statement at the bottom. Ugh. All right, I know that description of what goes on is kind of nasty, but hopefully this makes at least a little bit of sense. So the real key here is that every step along the way, we update the maximum value if we are trying to move to the left, and we update the minimum value if we are trying to move to the right. And then we progress through the tree, and if any node ever starts to return a value of false, we then enter into this false case right here, and then that kind of cascades back up, and we eventually return false from the entire stack of recursive function calls. Now, last thing I want to do is check out our tests. It looks like they are passing here. So I think you can agree with me that this is a nasty little bit of recursion, and it's one of the things that is kind of, and maybe not kind of, but very challenging to come up with on your own. But as soon as you see the solution, it's kind of like, yeah, okay, I guess I can take that. So hopefully in an interview setting, you can at least try to, discuss or talk your way through what is supposed to happen here, and then eventually get a solution up on the board. So this is definitely a tougher one, but like I said, it is probably one of the more challenging problems that you could expect to see, especially around binary search trees, which are only occasionally asked in interviews, or at least from what I've seen and what I've collected in a lot of research on common questions. So we at least have a better idea of what's going on with this solution right here. So let's take a break and move on to our next question in the next section.